Okay, so thank you very much for your time today and for giving me the opportunity to speak to you about XPRIZE Quantum Applications and specifically about advancing quantum algorithms for real-world impact. And I will get into this a little bit, like why this is very important that we are trying to tackle that question for real-world impact. So obviously quantum computing can have applications that are more industry-based, right? But then also quantum computing can have applications for changing the world for better. For example, developing new materials that can help sequester carbon, for example. So these are just some examples, but I just want to point out that my talk is really about this real world impact and why should we care. So the agenda, I just have pretty much 3 things I want to cover today. So why quantum computing? And I'm going to give it a little bit of a kind of like why, then build up to it, why the XPRIZE Quantum Applications. And then pretty much a little bit about the XPRIZE Foundation, so you get an idea about competition incentives. So why we have kind of like a competition as an incentive for people to push technology. And then we can go into a Q&A to answer some questions. So many of you know why we should care about quantum computing, and pretty much it all starts with current HPCs and our technology. So your laptop, your cell phone, or whatever is based on transistors. They have 0 and 1s, and we have successfully increased our ability to have certain floating point operations per second, right? So we are 10 to the 18. It's kind of keep growing. We make great chips. We have our GPUs, our CPUs. They work together depending on what compute you're doing. And these supercomputers are really pushing what we can do, right? And now we have AI coming in, so it's a very exciting time. However, there are some problems that are, even though you can implement them on these machines, if you would do them exactly, for example, material science, a lot of our calculations are approximate. Because if you would do them exactly, it would take a really long time. So we need to, for certain applications, we need to have a different way of compute, either to even access computations we were never able to do before, or to be able to do some applications, more precise or in a quicker, because it takes too long. So pretty much, as you have known, quantum computing was put forth as a way of computing, which is kind of like adding to the classical computation. We have a lot of different modalities, and theoretically, potentially, you could do 10 to the 23 operations per second. If you have run a computation on a quantum computer at the moment, that's not the case. You can do way less operations during a second. But if we have all the kinks and everything worked out, potentially we could do more operations on a quantum computer than what we currently can do on a classical computer. But there's still a lot of headway to do. Obviously, we've got a lot of different modalities. You have, your superconducting, your photonics, your trapped ions. You have your NVD crystals, you name it. We have a lot of different things. And for people who use the quantum machines, building them is one thing, but then operating is another thing, right? So as you know, what you learn about quantum computing is that you have to think about superposition, interference, entanglement, and all of the other key concepts of quantum computing. And you have to bring them together and understand all these technicalities in order to program a quantum computer, in order to develop a quantum algorithm. And it's actually not that easy. It's pretty hard to develop a quantum algorithm that then can be run on a quantum computer. And here, you may know about this kind of full stack idea, right? So when we talk about theoretically, a quantum computer could do 10 to the 28 or whatever flop operations per second, you have to understand that that's just potentially what we can do. But really what we have to consider is the whole entire quantum stack, right? So I just want to show you here the quantum stack where you have at the top the application, use case, right? And then you have to encode that into a quantum algorithm. And then this quantum algorithm has then be kind of even make simplified, right? in order to be represented and be able to eventually be run on the bottom, which is actual quantum hardware. And there's a lot of layers you have to go through: architecture, control logic, control panels, like how do you, for example, ensemble trapped ions when they move around, right? How do you work on a superconducting device depending on which qubits are connected? And things like that you have to consider. And this significantly increases the time it takes for your computation, this entire stack. So we are working on this right now, trying to make it more efficient, make better qubits. But really what I want to focus on today is the top two layers, the applications. So applications for real world impact, right? For social good, that like the community, like everyone kind of cares about clean water, for example, more food, increase the food production, right? So develop fertilizers and such, right? So applications that have like a big impact for our society. And then kind of like what kind of algorithms would we need in order to run these applications, right? So we'll focus on the top of the stack. So when I tell you right now that we are not quite where we want to be at the moment, I want to show you this graph. So here what you see is just kind of like the physical qubits. This is kind of an estimate out of a paper, assessing requirements to scale to practical quantum advantage. This paper discusses the challenges and the requirements to scale a quantum computing system, right, to achieve practical quantum advantage. So quantum advantage now, that is, like I have another slide where it shows, but pretty much from all the sense that we're seeing, it takes a quantum computer less time to compute something that a classical computer can do, or a quantum computer can compute something a classical computer can't, right? That's a quantum advantage in the kind of like, in a sense, that kind of like covers a lot of different areas. But pretty much what it illustrates here is that you have, depending on what you're doing, if it's factoring or quantum chemistry, and depending on what modality you have, right? It might take less or more physical qubits, or it might take less or more time to do the computation. But you can see anywhere in this case, we are like have hundreds of thousands of qubits, physical qubits, right, to millions of physical qubits. And computation in quantum chemistry could take weeks, months, years, right, to do if you want to do something very precisely. So we need to, like, as a community working in quantum computing, we need to push this. We need to push this down, right? Our qubits have to be better, have to have higher fidelity. We have to come up with better quantum error correction codes. But we also want to make sure that we not just push it down, like have less requirements on physical qubits, but we also want to make sure that the algorithms are more efficient, right? So that we actually have a quantum advantage that moves the time needed to do a computation, also like decreases that. And when you talk to experts, they think about this plot, for example, experts in the sense of like, when should I think about quantum computing rather than classical computing? And what I show you here is two different lines, the straight line, just by scale. I just scaled it. There's no specific reason here. This comes out of a very nice paper. So they just scaled it for comparison. So you have the quantum computer, which is kind of like your yellow, orange line, which is straight line, and the classical computer, which kind of have this exponential increase. And the idea here is that quantum computing at a lower number of inputs might be slower than a classical computer, but eventually there's going to be this crossover point because a quantum algorithm just scales more, like better for the specific problem than the classical algorithm does. And eventually there's this crossover point where a quantum computer could potentially run a calculation faster than the classical computer, right? Obviously, depending on what you're doing, you might want to push these curves in a different way, right? But there's going to be a crossover point. And then where is this crossover point? And then obviously, there's also going to be some investment someone has to put into in order to quantum computer. So this crossover point, probably you want to move a little bit, because you have to invest in a new technology, and you also have to consider that. But this is kind of the idea. So when the XPRIZE Quantum Applications kind of was developed, the idea that a computation shouldn't take more than weeks, right? 1 or 2 weeks, because else maybe it takes too long to do. now I want to go back to one thing I want to say is that even though we have developed many quantum algorithms, right? We actually are kind of stuck with some quantum algorithms that have been developed like decades ago, and they have developed these tools and these schemes of doing computation, quantum computation, and we haven't really like made much stride on this. So we really need something new in order to push this technology at the moment. So what I show here is that, again, from a very nice review work, which you can access, and I gave you the link there, or the reference. But in essence, like depending on what you're doing right now, you can do like different variational quantum eigensolvers, for example, or you can do like, like some kind of like convolutional networks, depending where you are here. We know kind of like the speedups we could have theoretically, right? So these are theoretical speedups, have not included all of the runtime that is needed on a computer, potentially in a classical computer, going through the whole stack, because I told you it takes time, right? So we want to consider it too. But in principle, you could have different speedups. So it is thought at the moment, if you talk to experts, that a quadratic speedup over a classical algorithm may not be enough. So you may need super polynomial speedup in order to actually outperform classical compute over the entire stack. So we really need to figure out what to do here. So all of these algorithms have been developed over the years, have been pushed to be more efficient and so on, but we're still not at the point where we can say we have quantum advantage for like some problems that are really like impactful for the society. We are starting to make improvements and use cases. You're moving forward, but it's just not fast enough potentially to really have the impact and make sure that the industry as a whole keeps moving forward and keeps getting the funding and so on. So obviously there's many use cases one could walk through, and I know that there are like a lot of programs that do this. And I just want to focus on molecular and material simulations, because I do believe, based on the fundamentals of quantum chemistry, and then it starts with the Schrödinger equation. It's just very naturally already in the quantum language, and these problems have a lot of potential to eventually be implemented on, for example, fault-tolerant quantum computers. So really, what I want to show you here is like, where are we right now for molecular and material simulations? So if you look at this speed up and how it works, so quantum simulations for molecular materials is a really good one. For example, right now, what we can do is we can simulate, some small molecules like LIH, right? BH2. So all of these, like, we can simulate right now, and we are somewhere in between of like making the small molecules right now. Like hydrogen, right, and beryllium hydride and so on, going on to like the larger molecules. And we can simulate them with 6 qubits, for example, beryllium hydride, simulate them with 6 qubits on an IBM machine, right, and we can learn something from it, obviously, because we want to learn how you take the classical approach and put it on a quantum computer. If you have done this, you know that actually a lot in this algorithm is classical. And then there is some part of the quantum, right? And then in this kind of like, when you're trying to find the ground state energy, you're in a loop and you're trying to like find a minimum, right? But in any case, there's a lot of classical compute that goes with quantum computing. So quantum computing is kind of like considered to be kind of like a computation that a classical workflow is just gonna send to a quantum computer, and then the information comes back, and then there might be some back and forth. But a quantum computer will not be working by itself. It's going to have a classical computer and a classical algorithm that's going to be part of it, likely, if you have worked with classical data. You can go over, and now obviously we can estimate more complex molecules. So what we are doing right now is try to study kind of the requirements we would want to need in order to do bigger molecules. So we're looking at the algorithms and trying to estimate, for example, how many logical qubits would we need for the FeMo-Co complex, right? So the iron molybdenum cofactor, I believe, if I said that's right. But in any case, like currently, like if you look at this work, you would need like over 2,100 logical qubits. You possibly need 4 million qubits, physical qubits, because they have to run maybe on a superconducting device. And it would take 4 days runtime to maybe simulate, that complex. So we are trying to, obviously, 2,100 logical qubits is a lot. We don't even have a single logical qubit that is 10 to the negative, has a fidelity of 10 to the negative 8, for example. We don't have that yet right now. So you can see that there's still a lot of work to be done. But in any case, we're trying to estimate now what we need for these things, for these kind of like, simulations, so we kind of know where we have to go. And then, but I do want to, like, even though I said that right now, right, like 2,100 logical qubits sounds a lot for a FeMo-Co, which is very important for fertilizer. I want to show you this data here. So here, I know there's a lot of data, but I want to focus you on the first column, for example, right? So the year, and you can see the year goes from 2005 to 2020. And then look at the last column, which is the Toffoli and T complexity. And you can see that initially it's an order of polynomial in n, right? But then it goes down to just order of n, for example. So I want to show you that over these 15 years, the complexity has steadily decreased, right? So we were able to like make big jumps going. So we're moving forward. We're making like strides, but it's just not the strides we would hope for, because we're still working with like tools. If you look at the tools here, kind of like trotterization, we're still working with trotterization, and that's kind of like an older idea, if you wish. So in any case, like we need really something that is new, something new in algorithm development that can push us in these different application areas. So what is the workflow for advanced quantum algorithm? Mukesh, I just saw your question here. So I am not an expert in quantum algorithm development. So I did not study quantum information science. But what I understand right now is that we work with classical data, for example, here, and you have a classical algorithm. Sometimes what people are looking for is in a classical algorithm how you go from the starting point, your data or whatever your input values are, to the problem you want to solve, and then you have different pieces of your algorithm, right, that you apply, like a for loop. I'm just saying something. You look up in the list. You're trying to minimize something, and for each of these things, you have an algorithm that does this part, right? So one approach is, for example, to look at this classical workflow, and somewhere you can, make this quantumness, bring the quantumness in the problem. For example, because even if you look at, for example, Shor's algorithm, a lot of it is classical, and then there is the quantum Fourier transform, right? For example, that helps to speed things up. So it really depends on how that flow is for advanced quantum algorithm development. There is one conference. It's called QIP conference. So Quantum Information Processing Conference. You can look that up. It's every year in February, and they have just wonderful tutorials, which is all recorded, and you can look up. And there are experts that talk about how this workflow for advanced quantum algorithm development looks like, if you're interested. Okay, so now let's go into XPRIZE. So why do we need XPRIZE? So pretty much, as we have seen, it's not just we've seen like we have made strides. It's very exciting, but 1,000, 2,000 physical qubits are fault-tolerant qubits are logical qubits are far away still. Like we might need millions of physical qubits, right? It still takes quite a long time, a couple of days to do a like even if you have a fault-tolerant quantum computer. So really, what we need to do is we need to push ourselves to come up with new ideas, and somehow find a path to come up with these new ideas to push this, because we want to make sure quantum computing will come to fruition. And how do we do this? So, excuse me, there's a lot of different ways, right, of doing this. One way is to do it through an incentivized competition. So XPRIZE pretty much is a 30-year old nonprofit organization, and it focuses on its incentivized competitions. So really much these competitions are put forward with a big prize purse in order for teams to get together worldwide and work on problems that really can inspire us and empower us to make breakthroughs, to accelerate a better place for us, like an equitable, abundant future for all. So this is kind of like the mission of XPRIZE. Excuse me. And it all started with the idea going back to 1919, when we had, aviation came up, and there was this price, $25,000 at that time, to go, from London to Paris with an airplane. And Charles Lindbergh achieved this. He got the prize. But it really sparked kind of the commercial aviation, right? But we needed someone to show that we can go this distance, and it's possible, right, to go over the ocean. We had to have someone who pushes that kind of like boundary, who is fearless and understands that there's a risk involved. And so kind of like XPRIZE sparked out of this idea. And the first prize was the Ansari XPRIZE. And pretty much it was awarded in 2004 with $10 million. And it was kind of like, can you shoot a rocket up into space at a certain elevation, and it comes back, and then you do it again. You do it again in a week or two. And really much we showed that it works. And it galvanized commercial space travel. And pretty much, Sir Richard Branson later acquired the winning technology of XPRIZE and built Virgin Galactic on this IP. So this gives you an idea of like what XPRIZE stands for. And excuse me, over all of these years, we have 30 competition, and we currently have 6 active prizes, because some like just finished. The prize purse, $150 million we have given out. Right now, the current prize purse, because we have 2 prizes with $100 million. So it's more like 350 at the moment. But in any case, you can see from the numbers, XPRIZE really helps to push things forward, accelerate innovation, and so forth. Pretty much, so why do we need an XPRIZE in quantum algorithm applications? So why we do this? So pretty much, I think you have heard probably from previous talks, or what you have read, is that kind of like we anticipate that we have kind of like quantum hardware that is capable of doing some quantum advantage by 2030. But the quantum hardware is increasing, but we haven't really made much progress in quantum algorithm development, especially for problems that are real-world application scenarios, right? So really what we care about solving for everyone to have a better life. And then obviously kind of quantum computing is kind of like certain areas have access to it. The talent pool is not robust enough, and collaboration is lacking. You may notice that every time someone says they have a quantum advantage, sometimes it doesn't, not every time, but it takes a couple of weeks or days, and then we have a classical algorithm that can do the same thing faster. So we have had that in the past, so now the quantum ecosystem has gone a little bit more careful about this. But I think personally this is based on not talking to each other, not understanding what the classical expert does for a certain application, and kind of having our quantum algorithm developers maybe sometimes work in silos. Not necessarily that's a bad thing, that's just because we are humans and sometimes we don't have time to ask the questions or have the right connections, right? So we really need to connect people with the right background in order to make this push. And XPRIZE can help with that. Then you have some other things listed here, why we need XPRIZE. So XPRIZE Quantum Applications is 3 years, started in March. You can still register for it till December 13th. Our title sponsor is Google Quantum AI, expert in quantum computing. And then we also have our presenting partner, which is co-sponsor, which is Geneva Science Diplomacy Anticipator, GESTA. Pretty much the idea is that, quantum has to be accessible for all, and we have to make the right policies as we develop this technology. It's a $5 million purse over the 3 years. It's in multiple phases, and pretty much all of the work and developed. This prize was developed with experts that helped us. So here's the advisory board, and then obviously the prize will also then be judged by judges, because XPRIZE is not judging. XPRIZE is staying out of the judging process. We have like experts that will judge the prize, and obviously we may add to this panel. Excuse me. It's because we want to have the experts and make sure that they can judge all the competition, the entries. So where are we right now? So here I just want to talk about the prize purse. So we have two prize purses or milestones. Phase 1, which ends December next year in 2025, will give out $1 million to the finalists, up to 20 that will share $1 million. And then they have another 1 year to like work on their solutions, and then winners will split, up to 3 winners will split $3 million, and then we're gonna have 2 to 5 runner-ups that will split $1 million. And that's in March 2027. And in between we have different milestones, but registration window is right now opened till December 13th. So here currently I'm just gonna give you an idea about who is in the competition. We have 260 teams at the moment from 45 countries. We are looking to increase the pool for the teams, because we want to make sure that we have the right teams in order to push quantum algorithm development forward, in order to have it applicable to real-world problems. And if you're curious about what the competition entails, it is fairly broad. So pretty much you don't have to run on a quantum computer, because we know that we don't have a fault tolerant quantum computer right now, and we will not have a fault tolerant quantum computer with the right number of qubits for a longer time. Just I told you, for FAMOCO simulations, you would need 2,100 or so logical qubits, which we don't have right now, and will not have in the next 3 years. So pretty much what this competition is all about is to push quantum algorithm development, come up with a new way of developing quantum algorithms, and bring them a more near term for quantum advantage. That's the goal. So you can develop a new algorithm that no one has developed before, and show it has quantum advantage, and it can be applied to a problem that is impactful to society. Or you can use a quantum algorithm that's already developed, but you can come up with a new application. So why do I say that? So the difficulty in quantum algorithm development to exhibit that speed up, and that goes back to the question another one we had, is you develop a quantum algorithm and you have this quantum speed up, and it's sometimes depending on the boundaries you set in your algorithm. So certain variables in your algorithm, I showed you this order, this table before, and there were n's and o's in there, and epsilons and kappas and yada, right? And these epsilons and these kappas all have certain range. And in a certain range, you can have to speed up over a classical algorithm. But this certain range now tells you that it can only have a certain application to it. So even though you have a quantum algorithm, you have quantum advantage for a certain range of these variables, right? For certain boundary conditions. Now the question is there an application out there for societal good, for example, that could work exactly in this range of your variables that are very unique and very tight and very specific? And that's why we need to have quantum algorithm experts, for example, talk to domain experts to understand in that problem space where it could happen. Or you can enhance performance. For example, we have showed you before, you need a certain number of physical gates, right? So you already have a quantum algorithm for a specific quantum application, but now you are able in that workflow where you have some part is classical, some part is quantum, you're able to quantify something more, make it quantum, the quantumness, increase the quantumness of your algorithm with a speed up, or you're able to use a different tool. Instead of doing traumatization, maybe you can come up with a new way of doing that step that speeds it up. So this is kind of the idea here with the different entries. It's very broad because we don't know where it's going to be heading to. So the competition is very broad, which is really nice. So pretty much what will judges look for, what's the magnitude of the positive word impact, estimated on the quantum resources, what's required for quantum advantage, and how near term is it? What is the strengths, of your support? So it's a very mathematical, theoretical submission for this XPRIZE. So it's different from other XPRIZes where you actually have to build maybe a gadget that sequesters a carbon from flue gas, for example, from output of a factory. This is different. This is really about, like a paper study, which is really nice. That way we can really have a worldwide competition, because it's theorists that start, but they have to talk to domain experts to make it happen, right? And then how novel is it? So the judges will decide based on a criteria of these. Why should you join? I get this question a lot. So why would you join? So really, if you join a competition, you're connected to like 240 teams, 260 teams right now. You have yearly drive impact. You're connected. Teams can merge. Teams can combine. You really can advance the field, and you really can be part of this kind of like collaborate network that we need to build in order to push quantum, right? And as a domain expert, it's good for you to connect to the quantum community. And for example, even if you're a domain expert, you may want to connect to a classical compute because you learn more from their side. So it's really about like, joining forces. And here I really want to emphasize, why do we need to join forces? So the winning team is really thought to have all of this expertise. Quantum information science in order to develop a new algorithm. Classical computing, right? You need to know when quantum advantage comes in, and you need to understand the best classical algorithm for this specific application. You need to know the domain experts, because they can tell you what specific, like regarding your parameters you need to tweak, or your boundary conditions, what would fall into that area? What specific problem could you solve given your constraints you have? And then obviously engineers, technical implementation, because you have to understand, kind of like how you would implement that, because you have to go through you have to estimate the resources, right? Resources needed in order to run it. What's the runtime to run your algorithm, right? So you need to know the stack in order to understand that and make that estimate. And then obviously also kind of have to know how far out it might be. And then really impact and social goodness. So this is where XPRIZE is going to help. So XPRIZE is trying to help with that. So if a team comes into phase 2, we'll try to help teams with social goodness and impact. We're going to have consulting firms to come in to help our finalists in order to understand that better, because that's something like scientists typically don't do on a regular basis. Okay, so I have a couple more slides and then we can go to Q&A, because I see more questions coming up. Team support. So obviously we try to support our teams through the process. We have team events, access to experts, our judges and advisors who can ask questions. Collaboration opportunities. We want really teams to get into this network. Even if you don't submit a winning solution, we hope that you increased your network and you now have access to experts you didn't have to, and you can combine forces. And then really help you also with translation and impact support. So if you are a winning team, XPRIZE is really trying to help you to accelerate your technology, find investors. So we would have investor summits of our winning teams come in and try to find investors for the technology and try connect them. So XPRIZE is a really big network. So we may have someone who is working in a domain that your quantum application is good for, and then we can connect you. Okay, so if you want to join a competition, I just want to tell you there's a couple of steps. where you can register for it. There's a $50 registration fee, but for people who are students or needs financial support, that can be waived. You just have to let us know. And then pretty much complete a competitor agreement, but that also we can give a little bit more time if there is more time needed in order to do that. So these are the couple of steps you need to do in order to join the competition. And pretty much, as I said, very excited that we have 260 teams, but we want to increase the competitor pool. We want to have more competitors, more people that join forces. Again, during the competition, you can merge with teams. Registration open till next week, December 13th. So please reach out if you're interested. Here's the email. You can find me also, for example, on LinkedIn. But this is the official email if you want to take a picture of this or screenshot and read over the guidelines so you get a better idea about the potential, kind of like how the competition looks like and more information about the details of how this is going. And now with this, I'm happy to do some answering questions.